So, which homework is going on? Homework 2 or homework 3?
Two.
Oh, still homework 2.
I didn't see him.
Yeah, that's because the plane wave. Yeah, okay. Yeah, so we have one more homework. So homework 3, I will post it probably today, and this will be due. Yeah, I was planning to post this earlier. This will be due on the day of the exam. Is that okay?
Yeah.
And 3, no, midterm 1, also on the same day. Yeah, so actually, yeah, I think the homework I did not post because I'll be working on it today. Like, I think the idea was Thursday we will work on it, so I was planning to post it on Thursday. Post it, okay. Yeah, for the exam, it's going to be mostly conservation principles, and I think you guys have taken the courses with me. I typically ask small pieces out of somewhere what you have already done. So if you had a very clear idea of what you were doing in the homework, there's a good chance that it should be fine. It should work out. Is that clear? If I ask a big question by any chance, if I decide to ask, then either I make it take home or I'll make it take home or something I will do in the course itself. And that is something that I've been considering. That's fine because we had I know all three of you guys have worked good enough. There is a chance that I might make it take home problem. So that raises feedback from you guys. Which one do you prefer?
Take home.
Take home. Take home is good. Yeah. Okay. So I haven't decided yet. Okay. So that I was saying I have a problem in mind, but I want to make sure that everything works out smoothly. So if it does not work out, then it will be the classroom problem. So
There is a question from green.
I haven't decided yet what to. How about this? I think, yeah, this was a feedback I received from, I think it was you guys, that sometimes it helps to work for the exam also. So let's have an exam where at the most I will ask, if there is a take-home part, I'll ask one question. If there is no take-home part, then I'll ask 4 questions. Typically 3 or 4 questions is what I ask. Okay. So one question is just so that you guys prepare and you. So preparation also helps you. What is it? Yeah, it's kind of bookkeeping, right? It helps you collect your thoughts. So it's like writing a paper, like you guys are all doing research. Often there is an argument, oh, why are we writing a paper? I did the work. But I think when you're writing the paper, you organize your thoughts. And often there's a significant amount of clarity in it. Another way is teaching, like often teaching, oh, it's not, sometimes you can argue that, oh, what's the point? I mean, you know everything. But often when you're organizing your thoughts, there's a significant amount of clarity, which is very significant. So yeah, so I would say this might be good. So so there will be at least one question of exam, but if I'm not able to fully frame that question, then I will be making a 4 question. Okay. And you asked Green's function. We did not really do Green's function significantly. So I cannot ask actually a Green's function problem. to you. Yeah, we cannot. Yeah, because Green's function, the way I have taught you, I think it was just the first lecture, right? It was just a motivation. You can actually solve serious problems using that app. And I haven't really taught you that, so I won't ask you. So it was mostly we were doing review, and I was motivating the notation that I will be using. So no Green's function. So basically conservation principle, mainly, yeah, just conservation principle. Let's keep that simple. There are good things you can ask. And small, I usually have small questions. If you know it, that's good. If you don't know it, then you struggle. That's what happens. Okay. So, yeah, here, what we want to do is, so we did do or used conservation principle in scenarios where you have medium, like we talked about a spherical charge distribution. We talked about planar charge distribution, and in your homework you also did 2 2-point charges, right? And one can mostly this is used in liquid, dielectric liquid. That's where this comes up, and there are these experiments. Yeah, one should appreciate this. When relativity first time came up, you could ask, so there is a capacitor, and if it was moving, how does the electric field transform? What is the effect of that electric field on this? So at that time, these experiments really used these facts. So they played an important role in the experimental verification of relativity. And paradoxes also, one can raise a lot of questions too. Another configuration where electric field comes up is a plane wave configuration, basically an electromagnetic wave. When light is moving, whenever we see this light, that's electromagnetic wave. There is electric field oscillating, but they are oscillating so fast that what's the frequency with which this oscillates? Electric field is oscillating, right? The light that we see is electric field and magnetic field, but they're oscillating. How fast they are oscillating? Any idea of that?
Gigahertz?
Gigahertz, 10 raised to 12 hertz, probably more, a little bit more. Yeah, 10 raised to 14, 10 raised to 15. That's the. You can think of wavelength, right? Wavelength, typically, you remember red light is. What's the wavelength of red light?
Yeah, 500 nanometers.
500, that's correct, about 680 nanometer. It's good to remember because that's the length you can see. Using visible light, you cannot go smaller than that. That's why we cannot see virus. That's why virus is so hard to study, because bacteria you can actually see. You sit and wait and see what they're doing. You know what they're there, which house they go visit often, so you go and kill them. But viruses, you cannot spy on them, so we have very hard time understanding them. So a plane wave, we would like to talk about this conservation principle in the context of plane waves. Like that's an electric and magnetic field. Let's say this is a whole room full of electromagnetic wave, and what can we do? So let's talk about the plane wave, like monochromatic plane wave. That's a configuration we will use in the future also. Once radiation comes in, this will come out very handy. The basic ideas that we are doing at some stage in the future, we will use it again. At that time, it will come as a one step. So knowing these things. So what is a monochromatic wave?
Single frequency.
Single frequency, and by single frequency means
Color.
single color. That's correct. So color means omega, right? That's what we mean. What about K? So what's the equation? So what's the electric field? What's the electric field associated with a monochromatic wave? What's understanding we have? Okay. So in general, this could be anything, right? Electric field in general could be any function. That's what Maxwell's equation solves that. Once this is known, I can Fourier transform this. Let's Fourier transform only in time, not in position, only in time. And then I have d omega over 2 pi minus infinity to plus infinity. And this is exponential minus I omega t times the Fourier transform of this. And what is the variable it will depend on, Fourier transform? Will it depend on R? I have not Fourier transformed R, so this depends on R. And what else does it depend on? Does it depend on time? It does not, because this is a Fourier transform. I have put in all the t dependence in this. This is omega. Fourier transform is in the frequency state. This is the amplitude of this particular wave. Right? It is like saying that give me a sound wave, I'll break it into sine waves. Like instead of sine waves, you're talking about exponential with sine waves in a sense. So, and you want to talk about this, right? This is the amplitude of this particular omega. So there is when you think about sound, each has a tone, right? That's your tone. Add up all the tone, and this is how much of each tone. Like that's the amplitude of each tone. So that's the way you want to look at this function here. And it's always Fourier transform are also, if necessary, if not necessary, that you Fourier transform. Yes.
Amplitude is vector.
Yes, amplitude could be a vector, right? Since there are, how do I mean? What do I mean by this? So what you have in mind is, let's say, typically when we think about a wave, right? So you would say this is a wave, correct? And then you would say that's an amplitude, and this is sine of omega t. And then you would say that's an amplitude. That's good. But now let's say this is a vector, right? So I have that. What that means is that is f1t I plus f2t j. And let's say that's your vector f of t. Right? That could be what it is. Now I can have various configurations, but so in principle, I could have this is a 1 sine of omega 1t, right? I have plus a 2 sine of omega 2t j hat. That's a possibility, but I want to consider those. So this is a choice I make, right? So in general, I would say that I want to talk about a situation where this is this. In that case, I can take that common and then say this is a 1 I hat plus a 2 j hat times sine omega t, and that's nothing but a sine omega t. Right. So in that sense, so this is the vector amplitude of this vector function, if that makes sense. Right? And like this seems like, oh, like I'm integrating over, so it seems like I made this assumption that omega 1 is equal to omega 2. That's not really an assumption because this is an integral, right? So I collect all omega 1s together, all omega 2s together. So it's not, I can always reshuffle. So it's not really, I mean, in this case, it seems like that's an assumption. But under the integral, it's okay. So I can always do that. Okay. So in that sense, that's it. Okay. Yeah. Yeah. Okay. So, but sometimes it is necessary only to Fourier transform in omega, and it is one would say that okay, what's the big deal of Fourier transforming? All the material properties typically are given in the frequency domain. Like when you say a dielectric material has some refractive index, it's a color dependent, or refractive index. That's refractive index is a color dependent quantity. You do an experiment, what's the refractive index of glass in for red light, for blue light, so on. So you know the frequency dependent. That's what experiment would tell you. So it is necessary to go into the Fourier space, and then you come back if necessary into the time. All the experimental responses happen in omega. So the frequency space sort of is necessary whenever you're interacting, but the position Fourier transform probably is not necessary, but sometimes it's convenient to do that. So if you do that, if you Fourier transform in the position also, so you do one more Fourier transform. And even in this, you have the choice that you leave x, y alone, only z is Fourier transform. All that is a choice you have, but let's Fourier transform all of it so that then we have all taken care of. So this then becomes the qk over 2 pi q and the omega over 2 pi. And this is e raised to I k, the vector dotted with r, and the other one already sitting there, that's I omega t. And now the Fourier transform of this is k now. Okay. Is that clear? I started from here and did 3 more integrals like this. The only question you, and the limit stays, since I did not write the limits here, I did not write the limits, so they're all going from minus infinity to plus infinity. In this definition right here, this 2 pi, you will see that it changes from books to book. When you go define your Fourier transform, everyone defines their Fourier transform in their own way. You can either put the 2 pi here or in the inverse Fourier transform. This is from position to Fourier space, and then there is a formula for the opposite. So it's just that it has to be balanced. So there could be a 2 pi here or in the opposite, and sometimes you put a square root of 2 pi, square root of 2. That's also, as far as square root of 2 pi is relevant, you will see that whenever you do quantum mechanics, you will see the square root of 2 pi. And that's because you want to give equal. There it is sort of necessary because you have this Heisenberg uncertainty relation, which is written in a particular manner. And then it is very convenient to write that as square root of 2 pi. But otherwise, it's just that it should not matter how you define your Fourier transform. As far as you're consistent, even in quantum mechanics, you can always move the Fourier transform 2 pi to one place, and that should be good enough. Is this negative important? Again, no, that's a choice. I can read, this is an integral, I can substitute omega to minus omega, right? That's perfectly fine. And then that you can change that minus omega to plus omega. But then that will enter into that minus omega. But that's a matter of definition again, whether you write plus or minus. And that's what I used here. When I Fourier transformed time, I used a minus. When I Fourier transform position, I used a plus. You notice there are 4 pieces in here. There are 4 Fourier transforms, x, y, z, and t. But it seems like when I was doing position Fourier transform, I used a plus here. This one I used a negative. Right? And you would ask, why would I do that? Anything you can think of? You'll always do it like this almost. Only a difference could be that you like sometimes put a minus here or a plus. But always you will see this way. So it's not necessary, as I said, whether I use plus or minus, it doesn't really matter. It should not matter. But this is a better choice. Can you think of something that would need a minus sign somewhere in between? This is a dot product. No, so K dotted with R is a dot product, right? In 3 dimensions. Now I'm having a 4th dimension in there, right? Omega T, and that too, yeah, that's it. Right? And so why would you have that 4th dimension? Where does 4th dimension go? Where does time come in? Relativity, right? And in relativity, so this you would say is a dot product. So this is K mu, X mu if you want. Right? So this will be a notation. And in relativity, you always have this negative sign inbuilt. If you remember your, if you've done relativity in some form, we will do relativity here also. We'll spend a good amount of time on it. And this negative sign is so that relativity is inbuilt in here. It's just, why would you do that? So again, it's a choice, right? So if you put a plus sign, there's nothing wrong in that, but relativity shows up in a very transparent manner when you write it in the K dot R and minus omega T form. If you don't write it, that's perfectly fine. There's nothing wrong in it, but it comes out in a very natural way. You don't have to go one more step to convert it. Okay, so that's that. That's all about the choice. Okay. Okay, so this is any electric field. Give me any electric field, I can Fourier transform. Right? But we are talking about a monochromatic electric field. So E or T. So let's say monochromatic. E. Monochromatic, as you said, has to be one color, right? This is the color. Frequency is the color. I want to pick one color out of this, and that's my monochromatic. If I pick one color out of this, that's just this fixed omega, right? One piece, and that's my amplitude. I will so let's say this is sorry, Fourier transform in K also. This is, I want to fix one out of all this infinite. I select one, and its amplitude. So let's say this is e raised to I K dotted with R minus I omega T, and in the front, so now since there is a special K, and I'm doing this integral, let me call this K 0 omega. That's just a fact that I fixed my K. Whenever I leave that K open, that gives the suggestion that, oh, that's a variable. That's okay. It's just, if you want to really insist, oh, this is a special K now. This is the wavelength. This is the wavelength of the plane wave. This is the frequency of the plane wave. And it has an amplitude now. As we said, it could be a vector. It can depend on K naught and omega naught, but since K naught and omega naught are constant, I will just say E naught. So no integrals, we have fixed one. There's only one oscillation. It's like saying in music, there is a tone, there is special tone, there is only one. So that's it. Fine. Okay. And then you would say, oh, this is not okay. Probably it's not. Okay, because electric field is supposed to be real. right? Electric field should be real by construction because you make measurements of the electric field, right? So electric field is real, so that's not real, right? That's like cosine and sine. So I should make this real. So how do I make this real? So I can just say real part of it, or better, I will say this is complex conjugate. Right? So this is E naught. E naught. Oh, I should also say you will come across situations where in a medium, this amplitude could have complex. Okay, maybe the point is in a medium, electric field need not be complex because electric field is D, right? D is equal to epsilon times E. And this doesn't have to be real. But either way, if you're in position and time, it has to be real. I think that's a better way to say it. The moment you go into frequency space, it can be not real. And this usually you write in the frequency space. So in the position space, it has to be real. So no doubt about it. So even the amplitude cannot be. So let me, to make that real, so let me say this is, let me keep that outside. And raised to minus I R minus plus I. I added one piece, so divided by 2. Right, so this is real by construction, right? And what is this equal to? 1 by 2. It should be familiar. Cosine, right? Cosine. So this is equal to, and that makes it very clear that this is real. This is cosine of K dot R minus omega T. Okay, now. Okay. That all should be very clear. And again, whenever we do Fourier transform, it is good to work with exponentials because integrals are easier, exponential integrals are easier. But whenever we want to have a intuitive field, probably cosine is easier to do, but not. Maybe you're more comfortable with exponential, but it's the same idea, right? That's okay. So that's your electric field, and this is a monochromatic electric field now. One has to ask what is the magnetic field and so on. But before that, let's do the, if this, we started with an electric field and we talked about Fourier transform. Right? But now we are saying this is one piece out of it, but nevertheless, this is an electric field in position and time. What is its Fourier transform? So what is a Fourier transform of a monochromatic? So what is a Fourier transform of this? Now it's K, notice. Because I'm doing the Fourier transform. This is a parameter, right? Cannot omega. So what is the Fourier transform of this? You happen to know from your head? Out of your head? Okay. So if we don't know, we just do it, right? We just use the formula, right? What is the inverse transformation, inverse Fourier transformation? So that's your position to time, so, or position time to wavelength frequency. I had an inverse Fourier transform. So I had to integrate over dqr and dt. So dt, right? And invert this in the sense there are no 2 pi's because all the 2 pi I gave in the Fourier transform. So this is exponential minus I k dot. Notice the sign changing plus I omega t and E of RT. So that's the standard formula for finding the Fourier transform. If you know the function, this is how you will calculate the Fourier transform. So there's an orthogonality. involved in it, right? Should be familiar, right? So I have given you a special monochromatic wave, and I'm asking what is the Fourier transform, right? So this is known. So substitute this in there. Okay. So actually, let's go back here, and this is also good to think of this as real part is cosine, right? So this is also okay to say this is 1/2 real part of E naught e raised to I k naught. Right. Notice this is just a lazy way of writing like this. It's this real part basically allows. And the main idea is that most of what happens here is the same as what happens here. I do the whole steps 2 times. It's less clutter and so on. Okay. So if I want to substitute this in here, I will substitute it in here. And at the end, the real part, I should always think of it as 2 terms. So that's equal to 1/2. Real part comes out. Does it come out? Probably not, right? I have to keep the 2 terms. Okay, so it didn't help much. So I'll go back and do the same thing here. Because the real part I cannot take out, right? Because this has complex pieces in it. So, okay, so this is E naught can come out. There is no dependence in that. So that's E naught dqr T times. That is a half of, so I have to multiply this into this. Right? So let's do that. This is exponential, no, yeah. Yeah, 2 terms, right? This multiplied by this is exponential of minus I k minus k naught dotted with R plus I omega minus omega naught multiplied by time. And that's it, I suppose. Oh, but there is a second term, right? And plus, yeah, I think I have to write that. There's no way of escaping this. Minus I k plus, plus I omega plus omega naught T, doesn't there is a half. Good. Oh, it fitted in. What's this integral equal to? Cosine? No. So let's first do T integral, right? So let me ask you, what is e raised to, or let's do this dx e raised to I k x. It's just a x integral, but it's going from minus infinity to plus infinity. What is that equal to? Infinity, yeah, that's correct. You're saying that. Is it? Let's see. So this is some function. This is something like this, right? And I'm finding the area underneath this. Right. So it's plus minus plus minus plus minus.
Should be 0.
It will be 0. Right. 0. So here is the point. This is a hand waving argument. If k was not 0, if k was not, let's start with saying that if k was 0, then what is it? Integral. if k was 0. If k is 0, exponential of 0 is 1. Integral of x, that's surely infinity, right? So this is infinity when k is equal to 0. Correct? If k is not equal to 0, I can use this argument, which is not really a nice argument because it's plus 1 plus 1 plus 1 minus 1 plus 1 minus 1. If you go all the way to infinity, it's not very clear it is 0. But suppose I suggest that that's 0. One has to do this more rigorously. Otherwise, that's k not equal to 0. This should remind you of something. Where else do you see something that goes to 0 everywhere except at one point? Dirac delta function, right? So this is a Dirac delta function. It is a representation of Dirac delta function. In fact, this is 2 pi times delta of x. Delta of k, x is integrated out. Okay, so whenever you get an integral like this, it's a Dirac delta. If you want, can start with Dirac delta function and do various things. But let's not spend time there. And this is slightly hard to convince in a very rigorous manner that that's what it is. But it's the Fourier transform. So this is the Fourier transform of Dirac delta function. Any function, Fourier transform, right? This is the Fourier transform of the Dirac delta function. In quantum mechanics, this comes up very nicely. That's where you see. So, what is the integral of this? There are 4 exponentials here, right? And each of them can be done because it's an integral of the Dirac delta, right? So that's equal to E naught, right? So this is 2 pi raised to 4 and now again I will write this. So this is delta Q of k minus k naught. It says that it's omega. It's omega naught. Plus the same idea. Okay. So a monochromatic wave, basically the idea is that you say that, oh, it's not all the frequency. What is a monochromatic wave? You say that it's a very specific frequency. That's what you're saying. Omega is equal to omega naught. It survives only when omega is equal to omega naught. At one frequency, that's your point in here. And there is an omega equal to minus omega naught. Whether you're in the negative frequency or in a positive frequency, doesn't matter. It pretty much behaves the same way. When you think of sine wave as a complete set of functions, there you will see that sine of omega d and minus omega d are pretty identical. Right? So this is the completeness relation coming in, and that's why there is 2 pieces in it. But in the Fourier space, that's your monochromatic wave. Okay. So what is if you have a monochromatic wave, physically again imagine that there is a wave extending all over. Where is its position? If you want to recognize that, oh, where is this? There should be one special position. Right? The average, huh? No, think of a wave. A point charge is a material, right? I'm thinking of an electric field. Imagine this. And now I want to associate a special point to this wave, which is really extending to infinity. Is there a special position? Right? There is no special position, right? If I were to say, where is this monochromatic wave? It is everywhere, right? But when it comes to frequency, it is very precise. It has a very specific frequency. I can now switch this, or this is a momentum, right? It has a very specific momentum. Like a plane wave is something whose position I don't know, but I know its position very precisely. Think of quantum mechanics. Like momentum is known precisely. Position, I don't know where it is, right? You can flip the whole thing again. I can say that position is very precise. Momentum will be all scattered, right? What is that meaning? That's the particle. When you were saying there's a point charge, right? A point particle would be, or a field that is confined in if this was a delta function, then I don't know its frequency, because then this would be all, it would be a sum of all frequencies. And that's what you exploit in quantum mechanics, that either the position can be well known or the momentum can be known. When the position is not known, that's called a monochromatic wave. When the position is confined and the momentum is completely arbitrary, what is it called? When the position of light, an electric field that is really confined to a point, what will it be called? Photon. Right, that's it. That's the idea of a photon, but then it's momentum. It's not very. So that's a way to look at it when you confine. Yeah, but then you'll have the whole sum here, right? If this was a delta function, then by construction you will have a full integral of this. So it's built out of all this data. Okay, so that's your electric field, and that's what we want to work with now. What is a magnetic field? Right? If this is my plane wave, do I have a choice in the magnetic field? And if you remember in your often elementary, or not elementary, because the way of looking at it is that a monochromatic electromagnetic wave will be like this, right? So there's a straight line going, and that's your electric field. Right? And that's your electric field. So these are all vectors. With all the vector signs in them. Where is the magnetic field in here? Perpendicular to it, right? So it has to be this way. And when it is perpendicular, it can be the other way also. So let me choose it this way. And can there be a phase difference between them? It's so figure out if there is that phase difference allowed or not. Like suppose you say that is a slight, like magnetic field could start from here, right? But I'm going to start from here. So that's your magnetic field. That's you've seen this. Right. Okay, that's your magnetic field. The question comes: can this magnetic field and electric field have a phase difference between them? Okay, and that's a quiz problem. Figure out or check out, can there be a phase difference between that or not? And in fact, we will see if at all you raise such a question, how do you answer those questions, right? It's always the Maxwell's equation. Does Maxwell's equation allow that phase difference? That's good. Usually, whenever there is an oscillation, this is not really an oscillation, right? That's a wave. What's the difference between a wave and an oscillation?
Where is it?
Wave is energy. Oscillator also has an energy, right? Wouldn't you see that? I can think of, huh?
That is the result of an
No, like I would say oscillator has an energy, right? You can write the energy of an a mass that is oscillating, right? It has an energy, kinetic energy and potential energy. So yeah, energy can be there for both wave and oscillator. The main and whenever you have an oscillator, there is a time dependent quantity, right? There is a mass, it oscillates in time. What about its position? That's its position, right? Its position changes a little bit here, but it's always center point is very fixed. It has a fixed position. How do you construct a wave out of an oscillator? A wave is an oscillator at infinite point, right? So this is, for example, this could be your X, right? At each point, it is oscillating in time. At each point, it is oscillating in time. And at each time, there is an oscillation in X also in that. What is it? If I were to, so this is a snapshot in time. So notice at a particular time, there is an oscillation. So there is an oscillation in the sense there is a dependence. So for example, lambda will be here. This is lambda. The periodicity, the periodicity in position at fixed time is wavelength. The periodicity in time at fixed position, I can say X, you fix X, so you pick one point, and there if you allow time to go, this will go down, up and down, right? There's a periodicity in that. And that's frequency, right? That's your 2 pi over time period, if you want. And there could be a connection between the lambda and the frequency. It's not necessary for every wave, but typically there is a connection, and that's the velocity of the wave. So, so this is a wave in that sense, and whenever there is a wave, it turns out that there is an energy that is there is a flux of energy. So for example, here there is more energy than at this point, right? Because it is on a higher level, if you want, if you think of it as a water wave. And then as time evolves, this will change. This will move to the right. The maximum point of energy after next second, it will be here, and it keeps moving. So there is a flux of energy. In fact, there is a momentum also. And that's a very significant property of a wave. If you say there is a movement of energy and time, there's a flux of energy, and there is a momentum itself associated with it. There is a special direction you take, and you say that's K. That's your K naught. Which turns out, so you can say this is a unit vector. You can write the vector K naught as 2 pi over lambda times the unit vector K naught, and that's your vector. So wavelength is associated with the direction. So there is a very special direction for a wave, and there is a wavelength, and that's how you define your K naught in this. And K naught is always got by the right-hand rule of E cross B, right? But why all this? Like, is that who dictates that? Like, is that a choice I make in monochromatic waves? Here, this was just a choice, right? I said, out of all the electric fields, I'm going to build one out of it. But here, there is no choice. I'm going to show that this is done because Maxwell equation has to be obeyed. Why is the magnetic field here? Can it make an angle? Right? It will come out that it has to be perpendicular. So let's see how we go about this. This is in Fourier space. It seems like a good idea at this stage. Why not write Maxwell's equation itself in Fourier space? Right. So let's go back to Maxwell's equation, write it in Fourier space, and then interpret it. So let's have Maxwell's equation. We have divergence charted with electric field of T is equal to epsilon naught, right? Let me write the epsilon naught, the constant. That's Why not write it as B? This is B. It's equal to rho of RT. I want to Fourier transform it. And I want to Fourier transform. Usually you would say, I want to go from here to there, but use this, right? If I know the function, I can Fourier transform by doing this integral. So I'm going to multiply by this exponential and then integrate. So I'll do that. Whatever I do on one side, I have to do it on the other side also. So do integral dqr and integral dt. Right. And all these minus infinities are understood. And this is e raised to minus ik dot with r plus I omega t. I'm only using the Fourier transform. I'm not working with monochromatic wave yet, so I don't have this complex conjugate now. I'm just doing Fourier transform and do this delta t. So this is position, right? T r comma t. But whatever I do on the left hand side, I have to do on the right hand side. What is the right hand side? Basically a definition. So what's the right hand side? Maybe here. What is it equal to? What will I write here?
Rho of k.
Rho of k. It's a Fourier transform of the charge distribution, right? That's the definition. So it's k omega. I do the same thing here, right? But I have to be careful. Now that's tricky, right? How do I do this? This is a gradient of that. So somehow I cannot say this is a Fourier transform of gradient of dk omega, because gradient is with respect to r and I'm integrating over r, which r. Right? So I have to handle this gradient somehow. I do integration by parts. If I do integration by parts, this will come and hit on that. There will be a surface term, but on the surface, I'm saying there is no d. D goes to 0. We will talk about situations where they don't survive on the surface. Okay. So if I do that, so I can hit it on this. So this is minus of dqr dt. Gradient acts on the exponential plus I omega t and d r. Clear? There should be an when I do integration by parts, there's a surface term also. I'm dropping that, saying that d goes to 0 on the surface, which is at infinity. Like there is no electric field on the surface. What is the gradient of this exponential? Where does it hit? This gradient hits this r, right? So what is gradient of exponential of minus I k dotted with r? What is that equal to? Gradient of an exponential, any exponential function derivative is the exponential itself, right? but then I have to hit the argument of the exponential. Right, so that's the same as gradient argument. So I'll write this as R dotted with K and minus I. That's the way of writing it. Okay, minus I. This is nothing but 1. Right. 1 multiplied by K is just K. So this is equal to minus IK, which you could have seen it right away. Right? When I hit the derivative, it's a K. Okay. So this can be replaced with minus IK. Once it is a K, this is an integral in R. Right? Position, I don't really have to worry about K, I can bring it out of the integral. So this is the same as minus and a minus becomes plus. So this is I times K times d cube R et exponential of minus IK dotted with R I omega t d R t. That's equal to rho of K omega. And as a dot. This was a dot. Right? This dot is with this. What is this integral equal to? Not delta function, the C of RT, right? So again, the Fourier transform of D. Right? So this is I in dotted with E of K omega equal to rho K omega. That's your Maxwell's equation and Fourier transform. Notice this is very simple. This is not a differential equation at all. Right? It's not a differential equation. It's algebraic. It's just telling me that there is a, for every mode K, remember K was a mode, right? For every Fourier transform mode K, this has to be satisfied. It has to be perpendicular. The electric field and K has to be perpendicular for every mode. And sorry, it doesn't say that it has some. I said it wrong, right? If it is perpendicular, means only in an electromagnetic wave, right? If there was a source, it is not. Wherever there is no source, it is 0. Then that is perpendicular. Right? So that's what. So that's your Fourier transform. Notice how simple it was. What happens when you have, if you have any differential equation, if you're taking the Fourier transform, take a gradient, replace it with IK. That's your Fourier transform, always. So if you want to Fourier transform any equation, switch this to IK. And it always works as far as that all the boundary things are. It's much easier than the 5 steps involved. But it's the same 5 steps that you always do, and it always comes out of IK. Okay. What about sometimes your time derivative, right? What about time derivative? What will it do? If it was a time derivative here, right? If it was a time derivative, this will be a time derivative. When I integrate by parts, this will hit this quantity and it will bring me a plus I omega, that's minus 1 survives. The only difference is that I have put an I minus. So I don't have to do all these steps anymore. I can write my Maxwell's equations immediately. So Maxwell's equations then become I times K dotted with B is equal, so this is K omega equal to 0. Right, that's the second maximum equation. Third one is I K crossed with electric field not differential equations. These are not differential equations. These are just constraints on modes, if you want, is equal to the minus becomes plus I omega B K omega. And the fourth one is I K crossed with H. This plus becomes minus. And this is plus J. Okay. That should come out, that should be clear. Questions? John? Questions? This is the full Maxwell's equation, right? There is a special case that happens when rho is equal to 0 and J is equal to 0, and that's what means light, right? Whenever there is no light traveling, that means whenever you want a wave equation coming out, you want to set rho equal to 0 and J equal to 0. So let's say rho is equal to 0 and J is equal to 0, and let's see what happens. Yes, for sure.
I guess do like the opposite, where if you were to do the inverse Fourier transform.
Yes, if you do the free, so if you start from here, do the same integral, and you can pretty much go back, right? There is a K here, right? K can be written as a derivative, and that's a trick you always use. So whenever there is some parameter, you write it as a derivative. Then you can pull the derivative out, do the integral, and do it. So that's standard trick to use. There might be some constants you might miss whenever you're doing these things. You might miss a constant, but up to a constant probably you can trace it back. Because derivatives always miss a constant, whenever we're doing an integral. So up to a constant, this can be. Okay. Okay, so let's consider the case when rho is equal to 0 and J is equal to 0. Right? This is a Fourier transform. When I say rho equal to 0, it's a Fourier mode that I'm going to talk about. In that case, I have K, so dotted with D is equal to 0. K dotted with B that's equal to 0. Then I have K crossed with E is equal to omega times B, and K crossed with H is equal to minus omega times D. Right, that's a four Maxwell's equation. In if rho is equal to 0, J is equal to 0. Let's very quickly see what's happening in this diagram with this. Like if we were to say that's your K and that's your D, let's see if that works or not. K dotted with D, D is nothing but E itself in vacuum, right? That should be perpendicular, right? So that's the perpendicularity there. K dotted with B is perpendicular. That's also coming out, that's the second one. Next, let's see, K crossed with E has to be equal to, at least direction wise, has to be equal to omega. So K crossed with E, right? K crossed with E to the right hand, and at least direction wise, it comes out in the direction of omega. And K crossed with H should be in the K crossed with H goes in the minus electric field. So that all that seems to be correct. And you might wonder, oh, does this imply E cross B has to, we always say E cross B has to be equal to K, right? So can we see that coming out better? So let's do that here, right? So let's start with this equation and multiply with E, right? So let's do E crossed with K crossed with E. What is E cross B, by the way? Remember pointing vector, right? So that's equal to E cross with H is a pointing vector. So that's your omega. Actually, before we do this, let me do one more thing here. So this immediately tells me this is in vacuum, right? The moment you say rho is equal to 0, J is equal to 0. And let us also, let, right? This is an assumption at this point because this whole thing could be moving in a medium. I could have a huge medium and then this is happening. So let epsilon be equal to epsilon naught and mu is equal to mu naught. So that's just simplification at that stage. But if you, just for having some insight, in that case, we have K dotted with E is equal to 0. K dotted with B is H, right? So let me write it in B or H. Let me say B, right? B is equal to 0. That's K. Oh, K for my H. K crossed with E is equal to omega times mu naught times H. And K crossed with H is equal to minus omega times epsilon naught times E. Right. And we've said that, oh, let's see the flux, right? What is the flux now? Flux, remember, was E crossed with H. So I will do E crossed with K crossed with E is equal to omega mu naught times E crossed with H. So that's my S. The flux of S is equal to 1 over omega mu naught. And this is B cross. This is K times E squared. And the other term is a minus of E dotted with K times E. But K dotted with E is 0. So that's equal to, let me say, this is K over omega mu naught epsilon naught times epsilon naught E squared. Let's put a half, remember, half yeah.
Right, and you
Yeah, U, right?
minus
Yes, and U is equal to half epsilon naught E squared plus 1 by 2 mu naught mu naught is top, mu naught H squared. Right? But I don't have is that possible? Okay. Yeah, let's not use that. Let's just say here But we have mu naught times epsilon naught is c squared, right? Okay, so this is equal to c squared k over omega times epsilon naught. It will come out to be in terms of u, but it's not very obvious at this stage. Before that, I have to do a few things. Let's see. Yeah, here, if you notice, magnitude of h is using this equal to 1 over omega mu naught times k and e are perpendicular, right? K and e are perpendicular. So this is nothing but k times e. If k is perpendicular to e, the cross product will be just k times 1. So this is k times the magnitude of e. Right. Using this equation, the magnitude of e is equal to, second equation, magnitude of e is equal to, again k and h is perpendicular, so it's k over omega epsilon naught times magnitude of h. Right? So that's from the second equation. This is from this is from. But both, how can both be true? Right? If both has to be true, there has a constraint here, right? Let me substitute this in that, right? Then what I'm saying is that h is, so let me substitute e here, right? So this is k over omega mu naught times e, which is k over omega epsilon naught times h. How can both be true, right? So the only way possible is that this is equal to 1. Right? So we learn that k squared, that's c squared, right? K squared c squared is equal to omega squared, which is the famous k times c is equal to omega. That means that this is 2 pi over wavelength times c is equal to 2 pi over frequency. Use 2 pi times frequency. So you say lambda times frequency is equal to speed of light. Right? The wavelength of light times the frequency of light has to be equal to. That's a consequence of this Maxwell's equation. If this is correct, k times c is equal to omega. K times c is equal to omega now, right? If that is correct, I can actually put that in here, right? So this relation then, using this k times c, is nothing but you're saying electric field is equal to c times h. That's a connection. Because I could write epsilon naught here, right? And then epsilon naught in the numerator, and the curve. What happened? So, is this correct? Let me conclude this. No, it is c times b. So, yeah. So let's do this. Am I visible? Yeah. So h is equal to. So this is equal to k over omega epsilon naught mu naught times epsilon naught e. Right? Actually, let's not do that. Let me just move the mu naught on this side, right? So this means that b is equal to k over omega times e. K over omega is 1 over C. So this means that C times D is equal to E. Great. If that's correct, then the energy will be equal to C times B, right? So I can write this as B square over mu naught. E is the same as C times B. You can show that this is nothing but exactly the same. Energy is equal in electric and magnetic. Okay, so this will be nothing but epsilon times E squared. Half plus half, exactly equally distributed. Okay, I'm jumping that step so that I can complete. If that is true, come back here, that's your energy, right? K over omega is 1 over C. So that's your C times U. K over omega is C, and that is C squared. Yeah, so this is C times, and that is a K times. So the flux is in the direction of momentum, and this is C times. Check on this. The last thing that I am done. Yeah, I make a homework. Do these things. Is that clear? So idea is that the whole everything about the plane wave is basically the Maxwell's equation of itself. I have to hurry in the last piece because maybe I'll come back and fix this, or you'll see it in the homework. So it will be clear. Yeah.
Is that epsilon 1 or epsilon naught? Sorry.
Epsilon naught.
E squared. Okay.
Everywhere it's epsilon naught.
Okay.
So the way you want to interpret this is that when you say there is an electromagnetic wave, there is some energy in the electric field and some energy in the magnetic field. What fraction of energy is in the electric field and what fraction is in the magnetic field? That's a natural thing to ask. And the answer is that that's equally distributed. It's exactly equal.
For monochromatic.
For any electromagnetic wave, right? Actually, yeah, this is not monochromatic, right? This is one mode. Actually, it is monochromatic in the sense it is one mode of a Fourier transform because this is for a particular K, particular omega, right? This is, even though this is very general, Maxwell's equation is written, it comes out for each mode. Each mode satisfies it, like independently. I just did the Fourier transform and I thought, and if rho is equal to 0 and J is equal to 0, each mode has equal amount of energy, and mode by definition is the monochromatic wave. So it is true only for monochromatic wave, but any wave in the absence of rho and J, any function can be written in terms of modes, and each mode has electric and magnetic field equal energy in it. If rho is equal to 0, J equal to 0, that's the important. If there is a rho and a J, then there is a redistribution. Like that electrostatics, for example, purely charged, then you don't have a magnet. That's all. Yes.
This is kind of like a side question, but like, as far as like the colors and frequency of the visible light, like, is that discrete? Like, is there a number?
To our knowledge, it is continuous. Like it is really continuous. Now, what happens is that all this Fourier transform assumes that this position goes from -infinity to +infinity. but you will immediately say that there is a finite universe, right? So universe puts a limit on it, which means that there is a smallest length possible. That probably is related to the Planck's length that will come. So the moment you say that the universe is limited, so that will put a limit on the discreteness or a discreteness of K actually. So K has to be discrete, because the moment Fourier transform of a finite length is a discrete sum. Does that make sense? So when we do this, only when t is completely minus infinity to plus infinity does this come out to be a continuous integral. Otherwise, it's a sum. That sense. Yeah.
So it's wondered like the question of running out of colors or music notes. That's another way.
Yeah. Yeah. Music notes. Yeah.
Can you, given a certain time, can you have all music that could be possible, you know?
Correct. And I think eventually practicality puts a boundary on it and you will be limited in colors. But in principle, Maxwell's equation doesn't impose, these are classical Maxwell's equation, does not impose restrictions on colors. There is no selection process. In quantum mechanics, there is a selection. You have selected like discreteness is selection basically. But here at Maxwell's equation level, it's not. And to my knowledge, even when you go to quantum electrodynamics, it doesn't impose any selection on the colors. Yeah.
So if you added like just visible light, like is that
I guess it's continuous.
Yeah.
It's continuous. Yeah. To our knowledge, again, there's something putting a constraint. We don't know that.
If there is a field, it always still continuous.
It's still, if there is a field, it will always be continuous. To our knowledge, again, see, again, we struggle with all these infinities. One of the big problem is that our universe is finite, and or one of the arguments, someone who doesn't believe in infinity, easiest way to throw away infinity is that our universe is infinite, or sorry, finite. That puts a limit on that scale. Use that. But that's a very fine scale. So you don't, no one likes that because that's an unmeasurable quantity. There's a huge radius of the universe that puts a limit in there. So it's not a comforting situation, but that's surely a restriction.
I have a problem with the last step.
Yes. Oh, here. I thought you were showing me this. Yeah, okay. So that's, and what do you want? So,
I don't get the expression of regulations like this. I mean, the problem is with the half space thing. What is half space?
yeah, because you have to do this integral, like from here to here, it's not, what is this, 4 pi? R square, but what is that R?
It's the radius of question or something like that.
Yeah, what is that R? That's it. Right. So if you notice the problem, so there is this positive charge here, and there is a negative charge here, right? And we are dividing the space into two. Right? This is z equal to 0, and this is z equal to a, and this is z equal to a by 2. Right? And you're choosing this as a surface. You're finding the stress on this wall, if you want, imaginary wall. And this is z direction. Right? That means this is xy. Okay. So when I'm doing the integral, I'm integrating on this surface. So dA is actually equal to dx dy. Right? And this is electric field is a function of xy. So let me write it as u, right? U of xy. Okay. So when you say R, a convenient way of looking at this is, since this is symmetric everywhere, this comes out to be symmetric in X and Y, like actually this is equal to 1 over X squared plus Y squared plus I think A square over 4. I think some power, right? This is X squared plus Y squared. So that suggests that you can use polar coordinates. So what you can say is that instead of saying this is a plane, you can think it of a cylinder, right? And then think of a radius going to infinity. So this is actually, go to polar coordinates. This is R dr and d phi. 0 to pi, 0 infinity. Is that clear? That's the whole plane. And then do that integral, and then you will get that. So this is not R squared. This should have a xy. This has xy in it. Yes. Right, that's your xy in it. Yeah, E is there, so you have to square that. So substitute this in this, square it, and then you will get an integral of dx, dy, and this quantity. But d phi, there is no phi in this because this is R squared. Right? Yeah, that's 2 pi. Right, so that's 2 pi, and that R integral can be done. Right? And then you get whatever.
So the half space is not there.
This is the half space. Right, that's the half space.
0 to a by t.
0, no, not 0 to a, but minus infinity to a by t. Because if I take 0,
This is the z direction.
this is the z direction. Yeah. So this is z equal to 0, z equal to a, z equal to a by 2, and the whole space beyond this. Right? If I say 0 to a by 2, then I have to worry about the pressure on this side. That's harder. So I take it to infinity because the electric field goes to 0. Is that clear?
So that means minus infinity to 0.
Minus infinity to z equal to a by 2, but you don't come across that at all. Yeah, yeah, but that's correct. Yeah. Correct. Does that help?
Yeah.
Good. Could you finish? Okay.
Yeah, that's interpretation.
Oh, interpretation. What is that? What is that question?
Just to interpret this.
Oh. So what is happening is that, okay, so think of, so there is a sine theta integral, d theta sine theta, and cosine theta, and there is, let's say, x. Okay. And let's say 0 to pi. And if I were to do limit x tends to 0, this is infinity. Right? So I'm in trouble. But now the point is that if I do the theta integral, it is 0.
Yeah.
Right? So if this is a 0 multiplied by an infinity, what we are saying is that this is on the sphere. So there is a sphere, right? So divergence is equally distributed on the sphere. And whatever is the divergence exactly cancels out on that sphere. It's not a good, great argument. You shouldn't conclude much on it because there is an infinity sitting there, 0 multiplied by infinity. So it's very fishy argument, but that's the suggestion there. That you have this sphere before you take the limit, this goes to 0 means it is symmetric with respect to angle.
I would like this.
Then it can be considered a function. Direct a function on 0 function. If now the integral is evaluated first, and yeah, this is the as the integral is in right, and the result and the whole result. That's okay. This is good enough. Yes. As I said, this is a very fishy argument. So it's not a very rich. You cannot use this again. But yeah, the interpretation is that 0 is infinity can be killed. But in a more serious setup, that can be pushed. Is that okay? Like whenever you say that infinity is not good, that's the challenge. Like, is this really 0? Can this really be drawn? That's a very, like if I put it inside, it's not okay. But with outside, it is okay. That's kind of a fishy. But in this case, we are sure because we know that we can do it in an independent way. Right, so we are sure. Yes, Krishan? Yeah.
You emailed me about filling the grading to put 0, but I don't get the question.
I see. I see. So the point is, so let's say there is, let's say John, right? Okay. So let's say there is quiz 1, right? And the option is that you can leave this blank or put a 0. If you put a blank, that means that you're not penalizing the student. It is just excused. Like let us say there is, let's say this is 0, and then you get a 10. It was 2. So the average is 10 plus 0 is 10 divided by 20. That's what you do. But now let us say this is not 0. Right? This is now excused. So it is 10 out of 10. So that is 1, this is 0. So I want you to put a 0 right there. That's the way I have set it up. So that if there are students who get excused later on, then I can remove them. Yeah.
Thank you.
Good.